In this video, we're going to be talking about hypothesis testing using a single sample, specifically power and the probability of a type 2 error. Recall that a type 1 and type 2 error is that if our null hypothesis is true and we fail to reject it, the type of decision was made was a correct decision. If our null hypothesis is true and we reject it, this was a type 1 error. If our null hypothesis is false and we reject it, the type of decision was a correct decision. And if our null hypothesis is false and we fail to reject it, we've made a type 2 error. The probability that we correctly reject our null hypothesis is called the power of the test. Suppose that the student body president at a university is interested in studying the amount of money that students spend on textbooks each semester. The Director of Financial Aid Services believes that average amount spent on textbooks is $500 each semester and uses this to determine the amount of financial aid for which a student is eligible. The student body president plans to ask each student in a random sample how much he or she spent on books this semester, and then using the data to test with an alpha of 0.05 the following hypotheses. For our null hypothesis, that our mu is equal to 500 versus our alternative hypothesis that our mu is greater than 500. If the true mean is greater than 500, then we should reject our null hypothesis. But if the true mean is only a little greater, say like 505, then the sample mean might look like we expect it if the true mean were 500. Thus, we wouldn't have convincing evidence to reject that null hypothesis. However, if the true mean was $525, it is less likely that the sample would be mistaken for a sample from the population if the mean were 500. So it is more likely that we will be correctly rejecting the null hypothesis. The power of a test depends on the true value of the mean. Because the actual value of mu is unknown, we can't know the power of the actual value of mu, but we can gain insight to the power of mu by investigating some what-if scenarios. So let's consider a one-sided upper tail test. On the left side, we're failing to reject our null hypothesis, and then on the right-hand side, we have our rejecting our null hypothesis. If the null hypothesis is false, then our mu is greater than the hypothesized value. Giving us a power of 1 minus beta. Let's look at an example. So back to our textbooks. So suppose that our standard deviation is $85 and the sample size is 100. Now, since n is large, the sampling distribution of our x bar is going to be approximately normal. So what is the probability of committing a type 1 error? With an alpha of 0.05, if mu equals 500 is true, for what values of the sample mean would you reject the null hypothesis? This is where our alpha would go. So this is our rejection region. So we want to know what is the value of this x bar. So this is the z value with a 9.95 area to its left. That's the 1.645 because we already have that z value. So we're looking for our x bar. So we plugged in our 500, our 85, and our sample size of 100. So calculating that, we find that our x bar has a value of 513.98. So we would reject our null hypothesis for any x bar greater than or equal to 513.98. So we can write that down. Now, if the null hypothesis is false, then our mu is going to be greater than 500. So what if mu equals 520? This area to the left of x bar equals 513.98 That is our beta. So what is the probability of a type 2 error? So we'll have our z-value, and we'll plug in our values that we know, because we know x bar, and that gives us a negative 0.708. So we're going to look this up in the table of areas for z-curves. That's going to give us a beta of 0.239. So this area here is 0.239. So what is the power of the test if our mu equals 520? Well, the power is the probability of correctly rejecting our null hypothesis. Notice that the power is the same curve as beta. So power equals 1 minus beta. Again, notice that power is in the same curve as beta. So our power equals 1 minus beta. So here we'll have our power is 1 minus 0.239, which is 0.761. So if we reject our null hypothesis, then mu is greater than 500. So what if mu equals 530? Notice that as the distance between the null hypothesized value for mu and our alternative hypothesized value for mu increases, beta decreases and the power increases. So we're going to find our beta and our power. We'll have a beta of 0.03 and a power of 0.97. If the null hypothesis is false, then mu is greater than 500. So what if mu is 510? Notice that as the distance between the null hypothesized value for mu and our alternative value for mu decreases, beta increases and the power decreases. So we're going to find beta and our power. So plugging those in gives us a beta of 0.68 and a power of 0.32. Well, what happens if we use an alpha of 0.01? Look how much smaller that is. To the left is our beta, and to the right is our power. Beta will increase, and power will decrease. Now, what happens to alpha and beta and power when the sample size is increased? The standard deviation will decrease, making this curve taller and skinnier. The significance level, alpha, remains the same, so the value where the rejected region begins must move. The beta decreases and power increases. So what are the effects of various factors on the power of a test? The larger the size of the discrepancy between the hypothesized value and the actual value of the population characteristic, the higher the power. The larger the significance level, alpha, the higher the power of a test. The larger the sample size, the higher the power of a test. What about beta and the power for a t-test? Now, when using a t-test, the population standard deviation sigma is unknown. Beta not only depends on alpha and n and the actual value of mu, but beta also depends on sigma. So we must have an estimate of our standard deviation. The beta curves on the next slide, we'll see them. They can be used to estimate beta and the power of a test based on the value of D. And the value of D is the alternative value minus the hypothesized value, and that's the absolute value of that, divided by our sigma. So we're going to see absolute value of the alternative value minus the hypothesized value divided by sigma. Here are our beta curves. After you've determined beta and you've calculated your quantity D, you're going to locate D on the horizontal axis and move directly up to the curve for n minus 1 degrees of freedom, and then move over to the vertical axis to find your beta. So let's consider testing our null hypothesis that mu equals 100 versus an alternative hypothesis of mu is greater than 100, and focus on the alternative value that mu equals 110. So suppose that sigma equals 10, that n is 7, and alpha is 0.01. So we're going to begin by calculating our D value. So the absolute value of 110 minus 100 divided by 10 equals 1. We're going to use the degrees of freedom of 6 curve to estimate our B. So our degrees of freedom 6. We're going to find our degrees of freedom for 6 to estimate our B curve. So had a bit of a typo there. That should have been an alpha of 0.05. So we'll go over to our alpha equals 0.05 curve, and then over to a beta of 0.6. We're able to say that our beta is going to be approximately 0.6. And our power is going to be approximately 0.4. When the population distribution is normal, the t-test for testing hypotheses about mu has a smaller beta than does any other test procedure that has the same significance level of alpha.